Ever taken a really close look at a rainbow in an oil slick?
Or like, how can scientists even see something as tiny as an atom?
Yeah,
It's wild.
it's crazy. Well, get ready to unravel those mysteries because our deep dive today is diving headfirst into this super cool thing called diffraction.
You know, like when you throw a rock into a pond and you get those ripples spreading out?
Yeah, yeah.
Diffraction in action right there. It's basically how all sorts of waves, like light, sound, you name it, they bend and spread out when they hit something.
So it's like waves going a bit rogue, not just going straight ahead anymore.
Exactly. They go a little rogue, and this going rogue is what's behind so many cool things we see every day.
Now, those excerpts you sent over from Feynman's lectures on physics really got me thinking about this. He talks about picturing a bunch of these tiny antennas all sending out light waves at the same time.
Oh, yeah, Feynman, he was amazing at using these really vivid images to explain complicated stuff. He uses this scenario to introduce the idea of interference. It's how waves can either boost each other up or totally cancel each other out, all depending on how they line up.
Okay, so that's like a wave dance-off, where things can get really intense or totally chill, depending on their moves.
Precisely. When the peaks of two waves match up perfectly, they amplify each other, creating a brighter, more intense wave. We call that constructive interference.
Right.
But when a peak crashes into a valley, poof,
Uh-huh.
they basically cancel each other out, destructive interference.
So it's like waves can be best buds or like total frenemies.
Mm-hmm.
And Feynman uses this like funky shape and equiangular polygon to explain this.
You know, like a stop sign.
Oh, okay.
All equal sides and angles.
Uh-huh.
Feynman uses that kind of shape to show how waves from these multiple sources combine. It's what creates those bright and dark regions, those diffraction patterns you see.
He actually uses a stop sign as an example.
Yeah.
Now that is some outside-the-box thinking, but yeah, I see what you mean. Like, those patterns are everywhere, even the way a streetlight looks blurry when you kind of squint at it.
You got it. And here's the truly mind-blowing part. Even if each little light source is super faint, when you have a bunch of them all radiating together, you can create a really focused, strong beam of light in one specific direction.
So you're telling me those dazzling light shows we see, it's all because these little waves are interfering with each other.
It is, and this same principle is behind so much of how we understand the world, from the tiniest things to the most massive scales.
That's why.
Take diffraction gratings, for example.
You mean those pieces of glass with those tiny etched lines that can split light into rainbows?
Yes,
Oh, I used to be fascinated by those as a kid.
that's diffraction happening right before your eyes.
Yeah.
Those tiny lines, the scratches on the grating, they act like tons of tiny antennas, each scattering light. Because those lines are so close together, the scattered light waves, they interfere with each other.
So those vibrant colors I see, are they actually different wavelengths of light that are being separated out, like the grating is sorting the light waves by their color?
That's a perfect way to put it.
Wow.
And scientists use this very principle to make incredibly powerful tools.
Like what?
Well, like X-rays.
Okay.
They have a much smaller wavelength than visible light, meaning they can interact with things on a much, much smaller scale.
Okay, so we're talking tiny, tiny, tiny.
Super tiny.
But how does that connect to diffraction?
Scientists use those X-rays to actually see how atoms are arranged in crystals.
Oh, wow.
By shining X-rays at a crystal and studying how they diffract off the atoms, they can map out the crystal structure.
So we're basically tricking atoms into spilling their secrets just by shining the right kind of light on them and then seeing how it bends.
Pretty much. And it really shows how this whole idea of diffraction, it scales up to some seriously impressive tech.
Speaking of scaling up, you're not going to tell me those massive radio telescopes use diffraction too, are you? I mean, those things are huge.
They do. Just like those tiny lines on a diffraction grating, those big antenna arrays in radio telescopes, they're positioned just right to make those interference patterns.
Wait, so those telescopes are like giant diffraction gratings,
Exactly.
but tuned into radio waves instead of visible light.
You got it. And the cool thing is, this same idea in such different things shows a kind of fundamental limit. How much detail they can see, their resolving power. It's tied to both the wavelength you use and the size of your grating.
Nice. So if you want the really fine details, like
Yeah.
the structure of a molecule or a far-off galaxy, you need shorter wavelengths and a bigger grating.
Right.
Like trying to read tiny print, you need a good magnifying glass.
Perfect analogy. It shows why telescopes keep getting bigger and why scientists use all sorts of electromagnetic radiation, from radio waves to X-rays. It's all about harnessing diffraction to see the unseen.
It's like unlocking a secret level of reality, all thanks to diffraction. But this seems kind of theoretical. How does diffraction show up in our everyday lives?
You might be surprised. Remember diffraction gratings, the ones that split light into rainbows? You probably have a bunch in your pocket right now.
Wait, seriously? Where?
Think about a CD or a DVD.
Okay.
The way they shimmer with those rainbow colors, that's diffraction.
No way.
Those discs have tiny grooves etched into them to store info, and those act just like the scratches on a diffraction grating, scattering the light and making those cool patterns.
I always thought that was some special coating or something, not just physics doing its thing.
It's all physics. And here's another one you've probably seen a million times. You ever noticed how a point of light, like a street light far away, looks blurry when you see it through a tiny hole?
Oh, yeah. Like if I cut my hand just right.
That's it.
I always figured my eyes were just tired or something, not diffraction.
Easy to miss those everyday examples, but once you see them, you realize how common diffraction is.
So it's not just pretty rainbows and shiny CDs. Diffraction's messing with how we hear, too. You mentioned noise-canceling headphones before.
Exactly. Those headphones use teeny microphones to pick up sound waves, and then they make their own waves that are perfectly out of sync, basically canceling out the noise.
Wait, so they fight sound with more sound? That sounds kind of counterintuitive.
It does, but it all comes back to wave interference. When those out-of-sync waves meet, they cancel each other out, and you get peace and quiet.
That's wild. So diffraction isn't just about light, it's shaping our soundscapes, too. Is there anything diffraction doesn't do?
Well, it probably won't help you fold laundry, but it does play a role in something you probably use every day. Your wifey.
Hold on, my wifey router is affected by diffraction. Come on.
Real-world physics. Think about it. Your router sends out radio waves, which are electromagnetic radiation, just like light. And those waves, they can be diffracted by walls, furniture, even people.
So my comfy couch could be messing with my internet speed.
It's not about a single object. It's more how the whole layout of your home affects how those Wi-Fi signals spread and interfere.
Okay, so I got to find that sweet spot for my router to minimize interference and max out my streaming.
Exactly. A bit of diffraction knowledge can go a long way in getting your home network running smoothly.
I never thought of my router as a diffraction puzzle waiting to be solved. But you said something earlier that really grabbed me, something about Feynman and opaque screens with holes in them.
Oh yeah, that's where things get really interesting. Feynman loved pointing out those head-scratching parts of physics.
Okay, you got me hooked. Tell me more about these mysterious holes.
So picture a piece of cardboard with a pinhole in it, and you shine light on one side. What would you expect to see on the other?
A bright spot of light where the light goes through.
Makes sense, right? But it's trickier than that. We can actually act like the hole itself is the light source to figure out the diffraction pattern.
Hold up, how can a hole, which is nothing, act like a light source? My brain's a little fried.
That's the beauty of diffraction. It makes us rethink how we think about light. This weirdness is explained by something called Huygens' principle.
Huygens' principle. Okay, that sounds familiar, but I can't quite place it. What is that exactly? So, Huygens' principle, remind me what that is again.
Okay, so imagine that every single point on a wave, like the tippy top of a wave, acts like its own little source of new waves.
Okay.
These are called wavelets. So Huygens' principle basically says these wavelets, they all team up to make the next wavefront as the wave keeps moving.
So it's like a chain reaction of many waves. Light isn't just traveling straight. It's like each point saying, hey, keep this wave going.
That's a great way to put it. And that idea, that's what helps explain how light bends around things and makes those weird patterns.
Okay, I think I'm getting it. But why can we pretend that the hole itself is the light source? That still seems odd to me.
It's really useful for calculating stuff, for figuring out diffraction patterns, even when things get complicated. When we treat the hole like the source, then we can use Huygens' principle, see how those wavelets spread out from the hole and interfere on the other side.
So it's like a math trick that helps us understand all this wave chaos.
You got it. Diffraction isn't just about light going through holes. It's really about how waves act and how they mess with their surroundings. And that leads us to something else cool that Feynman talks about: edge diffraction.
Edge diffraction. That sounds even weirder than holes being light sources. What is that?
Okay, picture this. You have a super sharp edge, like a razor blade, and you shine light past it.
Okay, so light's doing its best to sneak around this razor-sharp edge.
Right. You'd think we'd get a crisp shadow behind it, right?
Makes sense.
But diffraction always throws us a curveball.
Let me guess. The shadow isn't actually perfectly sharp.
You got it. Instead of a clean line between light and shadow, we get these little fringes of light creeping into the shadow. And it's not just a smooth gradient, it's like bands of light and dark, little ripples coming off the edge.
Whoa, so the light bends around the corner? I always thought it went straight.
It mostly does, but
Right.
when it just grazes an edge, those wavelets from Huygens' principle, they don't just stop, they keep going. Those make interference patterns, and that's what causes those fringes of light.
Light's got a secret way around corners. Mind officially blown. Is edge diffraction actually important, or is it just a theoretical thing?
Oh, it's definitely important. Edge diffraction affects everything from how sharp shadows are to how powerful microscopes and telescopes can be.
Really?
It even changes how we see the world.
Wait, hold on. Diffraction's messing with how I see reality now.
Not quite that dramatic, but think about it. Have you ever actually seen a perfectly sharp edge, even under a microscope?
Now that you mention it, I guess not. Even the sharpest knife, it still has some tiny bumps and stuff.
Exactly. And because of diffraction, even those little imperfections scatter light, and that makes the line between light and shadow blurry.
Hmm.
Makes you wonder, if edges aren't ever truly perfectly sharp, what does that say about how we see the world in the first place?
Wow, that is a really good question.
It might mean there's a limit on how much detail we can ever see, a kind of built-in blurriness because of how light works.
It's crazy to think that something as simple as light going past an edge can tell us such deep stuff about the universe.
It is pretty amazing. Shows that even in the most ordinary things, there's a whole lot of complexity and wonder hiding just beneath the surface.
Well, I know I'm going to be looking at shadows and rainbows and even my Wi-Fi router way differently from now on. It's wild how something so important to physics is also so connected to our daily lives.
That's the beauty of physics. It's the science behind everything, big and small, even the things we usually take for granted.
Thanks to this deep dive, I don't think I'll be taking those everyday things for granted anymore. Until next time, everyone, stay curious. And remember, there's a whole lot more to the world than meets the eye, especially when you factor in diffraction.